the basic building blocks. But when you dive deeper into what makes up those protons and neutrons, things get, well, really weird.
They certainly do.
Because their fundamental parts, these quarks and gluons, they follow this strange rule. You just can't catch them alone. It's like the ultimate exclusive club.
That's one way to put it.
So in this deep dive, using the material you shared, we're going to try and get a handle on why that is.
Exactly. Our goal today is understanding this phenomenon called quark confinement. Why are these truly fundamental bits, the quarks and the gluons that bind them, sort of permanently locked inside other particles, these things called hadrons?
Okay, so let's set the scene. We've got quarks, the up, down, charm, strange, top and bottom ones. These are the basic bricks, right?
Right. Think of flavor as just their type, their category.
And they build hadrons, which you said come in two main types.
Pretty much. You've got baryons, which are three quarks together, like protons, that's two up quarks and a down quark, and neutrons, which are one up and two downs. You know, the stuff nuclei made of.
Okay, baryons, three quarks. Got it.
And then you have mesons. These are different. They're made of one quark and one antiquark.
An antiquark, so antimatter.
Yep. A particle with the same mass but opposite charge and opposite color charge, which we need to talk about.
Ah, yes, color charge. That's the key to the force holding them together, isn't it? The strong nuclear force.
Precisely. The gluons are the carriers of that force, the glue. And the charge they respond to isn't electric charge, it's this thing we call color charge.
Okay, let's be clear, though. This isn't actual color we see, right? It's just labels.
Exactly, just labels. We use red, green, and blue for the quarks, and then anti-red, anti-green, and anti-blue for the antiquarks. It's just a system, like positive and negative for electric charge, but a bit more complex.
3 types instead of 2.
Right. And the crucial rule is that any hadron, any particle made of quarks, must be color neutral or colorless.
How does that work? With 3 colors?
Well, for a baryon, you need one red, one green, and one blue quark. Think of it like mixing light red, green, and blue light together make white, which is neutral in this analogy.
Okay, so red plus green plus blue equals neutral. What about the mesons, the quark-antiquark pairs?
There, it's simpler. You just need a color and its anticolor. So a red quark pairs with an anti-red antiquark. They cancel each other out, color-wise. Green with anti-green, blue with anti-blue. Still results in color neutrality.
Okay, so everything inside these hadrons is balanced, color neutral. But why the lockdown? Why can't we just, pull one quark out? If we smash protons together really hard, why don't individual quarks just pop out?
And that is the absolute core of quark confinement. It's this fundamental rule baked into the theory of the strong force quantum chromodynamics, or QCD, that says isolated quarks and gluons just can't exist freely.
So it's not just that we haven't found one yet, it's that the theory says we can't.
That's the assertion, yes. And experimentally, despite, decades of incredibly powerful experiments trying to knock one loose, nobody has ever directly observed a free quark or gluon. Ever.
It's like they're stuck with some kind of cosmic superglue that gets stronger the harder you pull. That seems backward. Don't forces usually get weaker with distance? Like magnets?
Usually, yes. Electromagnetism definitely does. Gravity does. But the strong force is unique. At really, really short distances, like inside a proton, the force between quarks is actually quite weak.
Weak? Inside the proton?
Yeah, relatively speaking. It's a property called asymptotic freedom. It means when quarks are really close together, they act almost like free particles, barely noticing each other.
Asymptotic freedom? It sounds like a contradiction when we're talking about confinement. So inside the proton, it's all chill, but try to pull one out
and the force doesn't drop off like one away.
No.
Instead, it stays roughly constant, or maybe even increases a bit as you pull them further apart.
She's constant, so it takes more and more energy the further you pull.
Exactly. Think of it like stretching an idealized rubber band. Not a real one that might weaken, but one where the tension stays the same no matter how far you stretch it. The energy stored in it just keeps increasing linearly with distance.
Okay, so like a rubber band. But what's a band made of here?
That's where the flux tube or string model comes in handy. It's a visualization, right? Imagine the gluon field lines connecting two quarks. Because gluons carry color, charge themselves, and interact with each other. Unlike photons and electromagnetism, they tend to bunch together, forming a narrow tube or string of energy between the quarks.
Ah, so the self-interaction of the gluons is key. It squeezes the force field.
Precisely. It stops the field from spreading out like electric field lines do. So you get this tube, and as you pull the quarks apart, you're stretching this tube, pouring energy into it.
Okay, so you're stretching this energy tube. What happens eventually? Does it just stretch forever?
Yeah.
Or snap?
It snaps. but not in the way you might think. When the energy stored in the flux tube gets high enough, remember Einstein, E equals mc.
Energy equals mass times the speed of light squared.
Yeah, right. When there's enough energy in that stretched tube, it becomes energetically cheaper for the vacuum itself to spontaneously create a new quark-antiquark pair out of that energy.
Oh, wait. Creates new particles out of the vacuum just from stretching.
Yep. The flux tube breaks, but the new quark pops onto one broken end, and the new antiquark pops onto the other broken end. So the original quark you were pulling is now bound to the new antiquark, forming a meson. And the quark you left behind is bound to the new quark, maybe forming another meson or joining back into a baryon.
So you pull one quark, you stretch the tube, it snaps, creates new quarks, and you end up with two separate complete hadrons instead of one free quark.
Exactly that. It's a process called hadronization. You never isolate the quark, you just create more hadrons. It's like trying to isolate one end of a string, but every time you cut it, new ends magically appear on the cut pieces.
That's wild. So confinement isn't just a cage, it's this dynamic process that actively prevents quarks from being isolated by creating more confined quarks.
You've got it. And this has huge consequences. It dictates the whole structure of protons, neutrons, all hadrons. It's why we only see these color-neutral combinations. It's absolutely central to QCD and our whole picture of matter.
Okay, but is it always like this? Is there any way to break confinement? You mentioned something about Quark-Gluon plasma. Sounds like sci-fi.
It does sound a bit like sci-fi, but it's a real prediction of QCD. Under absolutely extreme conditions, think incredibly high temperatures, like trillions of degrees, or immense densities.
Like conditions we don't see normally.
Definitely not normally.
Yeah.
We think these conditions existed for a few microseconds right after the Big Bang. In this state, the Quark-Gluon plasma, or QGP, the individual hadrons basically melt.
Melt.
Yeah, the quarks and gluons are no longer confined within specific protons or neutrons. They form this kind of hot, dense soup where they can move around much more freely over slightly larger distances than inside a hadron. They're deconfined in that sense.
So the prison walls dissolve temporarily.
Kind of, and we can actually recreate tiny fleeting droplets of this QGP state today.
How?
By smashing heavy ions, like gold or lead nuclei, together at near light speed in giant particle accelerators, like the Large Hadron Collider, LHC, at CERN, or the Relativistic Heavy Ion Collider, RHIC, in the U.S.
Wow, we're making tiny bits of the early universe in the lab.
Essentially, yes. Studying how this QGP behaves, how it cools down and freezes back into hadrons, tells us a huge amount about the strong force and the nature of confinement itself.
That's incredible. Okay, so experimentally, confinement seems solid. QGP gives us hints about deconfinement. But what about the theory? You said it's a prediction of QCD, but do we have like a mathematical proof that it must happen based on the QCD equations?
That's the billion-dollar question. Literally, almost. While confinement is totally baked into QCD and everything points to it, getting a rigorous analytical proof starting just from the basic QCD equations is incredibly difficult.
Why so hard?
It boils down to how the theory behaves at the energy scales relevant for confinement, the sort of lower energy, longer distance scales. The equations become strongly coupled and highly nonlinear. Basically, the math gets ferociously complicated because the gluons interact with themselves.
So unlike electromagnetism, where photons don't interact with each other.
Exactly. That self-interaction makes QCD much, much harder to solve analytically in this regime.
So we're confident it's true, we see the effects, the theory predicts it, but the final QED on the blackboard is missing.
Pretty much. However, we have incredibly strong computational evidence. Lattice QCD uses supercomputers to simulate QCD on a grid of space-time points. And these simulations consistently show confinement emerging from the fundamental theory. They allow us to calculate hadron masses and properties very accurately.
So the computers say yes?
The computers say yes, very convincingly. And we have models like the flux tube model that give us intuition. But a pure analytical proof, that's still one of the great unsolved problems in physics and mathematics. It's actually related to one of the Clay Mathematics Institute's Millennium Prize problems, the Yang-Mills existence and mass gap problem. Proving confinement is part of that challenge. Wow. A Millennium Prize problem. Okay, that's serious. Yeah. Now, you mentioned earlier this idea of asymptotic freedom weak force inside and this super strong force when pulling apart. How does one theory manage both? You hinted at a running coupling constant. Right, the running coupling constant, alphas is the key. It basically tells you the strength of the strong force interaction. And the crucial thing is that alpha isn't constant. Its value runs or changes depending on the energy scale or equivalently the distance scale you're probing.
Okay. How does that work? Is it like electromagnetism? Does its strength change too?
Yes, actually, the electromagnetic coupling, alpha EM, also runs, but in the opposite way. In QED, quantum electrodynamics, if you get really close to an electron, you penetrate a cloud of virtual electron-positron pairs that pop in and out of existence in the vacuum. This cloud screens the electron's bare charge, making it appear weaker from far away. Closer in, the screening is less, so the effective charge looks slightly stronger.
Okay, so virtual particles screen the charge in QED. What about QCD?
QCD has something similar. Virtual quark-antiquark pairs also provide screening. But, and this is the critical difference, you also have virtual gluon loops because gluons carry color charge and interact with each other.
Ah, the self-interaction again.
Exactly. And these virtual gluon loops have the opposite effect. They cause anti-screening. They effectively amplify the color charge at larger distances.
Anti-screening, so they make the force seem stronger further away?
Precisely.
Yeah.
And in QCD, this anti-screening effect from the gluons actually wins out over the screening effect from the quarks.
Okay, I think I see it now. So if you're at very high energy, which means very short distances.
You're probing inside the anti-screening cloud. The effective color charge looks weaker, atoms become small. That's asymptotic freedom. The quarks interact weakly.
And then if you're at lower energy, longer distances.
The anti-screening effect really kicks in. The effective color charge looks much stronger. AS grows large, potentially infinitely large, and the force becomes incredibly strong, binding the quarks together. That leads to confinement.
So it's the running of S, driven by gluon self-interactions, that explains both why quarks are almost free inside hadrons and why they're permanently confined.
That's the picture, yes. The math behind it involves something called the renormalization group equations, which describe precisely how these couplings change with energy scale.
Mind blown. Okay. So we can't see quarks directly because of its confinement mechanism, but how did we even figure out they exist in the first place? What's the indirect evidence?
Oh, there's a lot. One of the earliest key pieces came from experiments in the late 1960s at SLAC, the Stanford Linear Accelerator Center. They fired high-energy electrons deep inside protons and neutrons.
Deep inelastic scattering.
Right, exactly, DIS. What they saw was that the electrons weren't scattering off the proton as a whole, but appeared to be hitting tiny, hard, point-like things inside. These were nicknamed partons initially.
Which turned out to be quarks.
Which turned out to be mostly quarks, yes.
Yeah.
And the way these partons scattered suggested they were behaving almost as free particles during the high-energy collision consistent with asymptotic freedom.
Right.
But crucially, no individual partons, no free quarks ever flew out of the wreckage. They were always bound up in new hadrons.
Right, okay, so DIS showed point-like things inside, behaving freely at high energy but still confined. What else?
Another big one is electron-positron annihilation. You collide an electron and its antiparticle, a positron, at high energy. They annihilate into pure energy, which can then rematerialize as a quark-antiquark pair.
Ah, but they can't escape.
Right. Confinement kicks in immediately. The quark flies one way, the antiquark the other, stretching that flux tube between them. Then hadronization happens, that snapping and pair creation process. What you actually detect are two back-to-back jets of ordinary hadrons spraying out in the directions the original quark and antiquark were going.
So the jets are like the footprints of the quarks.
Exactly. Sometimes you even see three jets, which is interpreted as the quark or antiquark radiating off a high-energy gluon before hadronization occurs. The angles, energies, and frequencies of these jets match the predictions of QCD incredibly well.
Wow. And just the fact that we can classify all the known hadrons, hundreds of them, into families based on simple combinations of quarks, baryons as QQQ, mesons as QQ, that must count for something too.
Absolutely. Hadron spectroscopy, the whole pattern of observed particles, fits perfectly within the quark model, which relies implicitly on confinement. It's a hugely successful organizing principle.
It's like we see their shadows, their effects, everywhere, even if we can't see them. Now, here's something else that really blew my mind from the material. The connection between confinement and mass.
Ah, yes. This is one of the most profound consequences, I think.
You're telling me most of my mass isn't actually from the mass of my particles?
Well, let's look at a proton. It's made of 2 up quarks and 1 down quark. The intrinsic mass of an up quark, the mass it gets from the Higgs field, is tiny, Maybe around 2 MeV-K. A down quark is a bit heavier, maybe 5 MeV-K.
Okay, so 2 ups and a down. That's what? 2 plus 5 equals 9 MeV-C.
Roughly, yeah. Maybe a tiny bit more with complexities, but in that ballpark. Now, what's the measured mass of a proton?
It's much bigger, isn't it? Like almost 1,000.
Yep, about 938 MeV-K.
Whoa. So the quarks themselves only account for like 1% of the proton's mass. Where does the other 99% come from?
It comes from energy. Remember EMCC? The vast majority of the proton's mass comes with the energy of its constituents locked inside by confinement.
What kind of energy?
Primarily 2 kinds. The kinetic energy of the quarks whizzing around inside the proton at nearly the speed of light because they're confined in such a tiny space. And crucially, the energy stored in the gluon field, the energy in those flux tubes binding them together. There's also energy associated with a sea of virtual quark-antiquark pairs constantly flickering in and out of existence inside.
So the mass of the stuff around us, the chairs, the planets, us, most of it isn't from the fundamental masses of the quarks given by the Higgs mechanism, but from the energy of these quarks and gluons being confined by the strong force.
That's exactly right. For the visible matter in the universe, the dominant source of mass is the dynamic energy generated by QCD and confinement. The Higgs mechanism only provides the tiny seed masses for the quarks. It's a really fundamental insight.
That changes how you think about mass entirely. It's not just stuff, it's confined energy.
It really is. And confinement has one more interesting consequence. It allows for possibilities beyond the standard 3-quark baryons and quark-antiquark mesons.
You mean other combinations that are color neutral?
Exactly. QCD doesn't forbid them as long as the overall color neutrality rule is met. So physicists have been looking for and finding evidence for more complex structures.
Like what?
Well, there are tetraquarks, which would be composed of 2 quarks and 2 antiquarks, and pentaquarks, made of 4 quarks and 1 antiquark.
4 quarks and an antiquark. How does that become color neutral?
It's more complex, but you can imagine combinations, like maybe a color-neutral QQ triplet bound loosely to a color-neutral Q pair, or other more intricate color configurations. The LHCb experiment at CERN has actually found several convincing candidates for pentaquarks in recent years.
Tetraquarks and pentaquarks.
Well,
what else?
There's also the theoretical possibility of glue walls, particles made entirely of bound gluons with no quarks at all. Since gluons carry color charge, they could potentially bind to themselves to form a colorless object.
Just pure force.
In a sense, yes. Identifying them unambiguously is tricky, though, because they can mix with ordinary mesons that have similar properties. And there are also ideas about hybrid mesons, which would be like a standard quark-antiquark pair, but with an excited gluon, contributing significantly to its structure.
So the particle zoo might be even weirder than we thought, with all these exotic possibilities allowed by confinement.
It certainly seems that way. Studying these exotic states gives us new ways to really test the details of QCD and understand confinement better.
Okay, so wrapping this up, this whole deep dive into quark confinement, what are the absolute key takeaways we need to remember?
I'd say number 1, confinement is absolutely fundamental to the strong force, to QCD. It's driven by the fact that gluons carry color charge and interact with each other.
Right, it's not just a box, it's a dynamic consequence of the force itself.
Exactly. Number 2, it explains why we never see free quarks or gluons, only color-neutral hadrons like protons, neutrons, and mesons.
And now maybe tetraquarks and pentaquarks too.
And hopefully glue balls. Number 3, this same mechanism leads to asymptotic freedom at short-distance shy energies, explaining why quarks act almost free inside hadrons and how we see jets in collisions.
The running coupling, constant doing its thing.
Yep. And maybe the most mind-bending takeaway, number 4. This confinement energy is the origin of almost all the mass of the visible matter in the universe. Mass from energy via EMC covert.
It really is amazing. Something we can't directly see shapes pretty much everything we can see, including its mass.
It's a cornerstone of our understanding of matter.
Well, this has been absolutely fascinating, trying to get our heads around why the universe locks away its most fundamental building blocks.
It's definitely a deep topic.
So as we finish up, here's something to chew on. Given that most of the mass we interact with daily arises dynamically from the energy of the strong force confining quarks and gluons inside protons and neutrons, how might that change our thinking about gravity? Does gravity just couple to this emergent energy mass in the same way it couples to fundamental mass from the Higgs field? Or are there deeper connections or subtleties we haven't grasped yet at the intersection of QCD and general relativity?
Ooh, that's a really good one.
Something for everyone to ponder. Thanks for joining this deep dive.
My pleasure.